Hello, welcome. In this video, I'm going to be working more related rate problems and working through the 4.3 extra practice. So, a sphere is expanding in such a way that the area of any circular cross section through the sphere's center, I'm lost an apostrophe there, is increasing at 4 square centimeters per second. How quickly is the sphere's volume changing when its radius is 3 centimeters? All right, well, I'm going to say, what are they telling me? The area of the circular cross-section. So if you've got a sphere like this, maybe I give it a belt to make it look a little more three-dimensional, and we think about a circular cross-section through the center, well, that's actually just going to be this thing right here. And it's going to be a circle that has radius given by, the radius of the circle. So what they're telling me is that the derivative of area with respect to time is positive 4 because the area is increasing. Okay, and we want to know what is the rate of change of the volume of the sphere when the radius is 3. All right, so we know a formula for area of that circle. That's going to be area equals pi r squared. So dA dt is 2 times pi times r times dr dt. And we're going to need to find dr dt because, well, I guess I'll just show you. If v is 4/3 pi times r to the third, and I am assuming that, for these extra practice problems for the homework or whatever, you can just go look up these formulas, these geometry formulas, so I didn't copy them onto the statement of the question. Okay, so this is 4/3 pi r to the third. So dv dt is going to be 4 pi r squared dr dt. We know what r is, we just need to solve for dr dt. So we know dA dt is 4 equals 2 times pi times radius is not 5 but 3. Times dr dt. So it's going to be 4 divided by 6 pi. But then over here, when I'm trying to find out what dv dt is, it's going to be 4 pi times r squared is going to be 9, times dr dt is 4 divided by 6 pi. Okay. So I've got 16 times 9. I don't know what that is, but maybe I'll say 4 to 6 is 2 to 3, and maybe that'll make it a little easier for me. 18 times 4 is going to be 72 divided by 3. Wait a second, that 9 and that 3, that makes 3 and 1, so 6 times 4 is 24. There we go. Eventually it would kind of fall out. All right. The second one is if w equals x squared multiplied by y, and x is decreasing 2 units per minute, and y is increasing 3 units per minute. That's kind of a lot. So I'm going to take all this down. dx dt is -2, dy dt is +3. What is the rate of change of w with respect to time when x is 4 and y is 5? Well, okay. I'm going to take the derivative of both sides of this equation with respect to time. And this is a product between x squared and y, so I'm going to have to use the product rule. So I'll take the derivative of x squared first. That's 2x dx dt. Leave y the same. Then I'll take the derivative of y and leave x squared the same. So I have all the pieces of information I need to find dw dt. I'm going to say 2 times x is 8 times dx dt is -2 times y is 5 plus dy dt is 3 and x squared is 16. Okay, this would be a safe place to stop. But if you felt like you had to go farther, you could say it was, okay, that's -80 plus 48 is, I think, going to be -32. Anyway, it's decreasing. All right. Surface area of a particular object is given by a equals e to the b, where b is the area of the base of the object. I saw this one. I was kind of just pulling some random related rate questions for y'all, and I saw this one. I'd never seen this one before. I don't know where this one came from. I don't know what kind of object is going to have surface area given by e to the b, but we'll just pretend that there is such an object. Determine the rate of change of the area of the base. So we really want to know what is dB dt. Surface area, that's dA dt, equals 10, and b is equal to 5. Right, well, dA dt, if I take the derivative of a equals e to the b with respect to time, that'll be, well, the derivative of e to the b is e to the b, but b might have its own derivative with respect to time. Right? So dA dt is 10 equals e to the 5 times dB dt, indicating to me that dB dt is going to have to equal 10 divided by e to the 5. All right, the next couple of them are, related to the same scenario where a spherical balloon is being blown up at a rate of 10 cubic feet per second, which means that the rate of change of volume with respect to time is positive 10. We're going to want to know how fast is the radius changing when the radius is 5 feet. Okay, well, v equals 4/3 pi r to the third. All right, so dv dt equals 4 pi r squared dr dt. And I've got all sorts of information here. I got 10 equals 4 times pi times radius squared is 25. So 4 times 25 is 100 pi dr dt. Makes me think that dr dt is going to be 1 divided by 10 pi. Okay. Then they're going to ask, this was number 4. Number 5, how fast is the surface area changing? Okay, well, the surface area of a sphere is 4 pi r squared. And no shame if you had to go look that one up. That one's one that's usually going to be just given to you in the statement of the question. Area is 4 pi r squared, so dA dt is 8 pi r dr dt. Fortunately for me, I just found dr dt in the previous problem for this scenario, right? I'm just going to plug in there. And so dA dt is 8 times pi times radius is 5, and dr dt is 1 over 10 pi. Okay, so I feel like that's going to be equal to 4 feet per second, 4 square feet per second, because it's a measure of area. All right. Number 6, the surface area of a sphere is growing by 20 square feet per second. How fast is the volume of the sphere growing when the radius is 2? Okay. So I got dA dt equals 20, dV dt equals what? Well, we know for a sphere, we've got this situation, we've done this a bunch of times at this point. And so I'm going to probably, in order to find dA dt, right, I'm going to need dr dt, okay, but they didn't give me in order to find dV dt, I need dr dt, but they did give me dA dt, and I'm going to use that to find dr dt and then substitute it over there. Okay, so 4 and 5 was kind of getting you ready to solve the type of question that's asked in number 6. So dA dt is 20, 8 pi, radius is 2, dr dt is what I'm kind of temporarily hoping to find. Okay, 20 divided by 16 pi. Okay, then I'm going to go over here and say that this is equal to 4 times pi, radius squared is going to be 4. Well, that's convenient. And dr dt is 20 divided by 16 pi. Well, the pi's are going to cancel. The 16 and the 16 will cancel, and that rate of change is going to be the 20. Hey, that was pretty nice. That seems too good to be true, that the area is growing by 20 and then the volume is growing by 20. I think that's just a coincidence. But, you know, with the fact that the way the formulas work here and that radius was 2, I think it just happened to work out perfectly. All right. Volume of water in a container is given by V equals 20H times 3 plus H squared. Find the rate of change of the volume of water in the container. All right, so we need dV dt. And that's going to be, all right, wait a second. Hold on. I'm going to rewrite this formula, right? I don't want to do the product rule on something that's going to be a polynomial anyway. V is equal to 60H plus 20H to the 3. So the derivative of 60H with respect to H would be 60, but the derivative of 60H with respect to T will be 60 times dH dt plus 60H squared dH dt. Okay, find the rate of change of volume of water in the container. Okay, yeah, so height is changing 1 foot per second. That means dH dt equals 1 and H equals 2. So 60 times 1 plus 60 times 4 times 1 is going to be 60 times 5 is going to be 300. The last problem we've got is number 8, a cylindrical tank with radius 2 feet. Okay, so it's a cylinder. Oh yeah, that's one that we have not really come into contact with at this point. That we probably should have, right? Cylinder is a pretty common object, especially in physics. A cylindrical tank with radius 2 feet is losing water at a rate of 4 cubic feet per second. Or maybe it's got a hole in it and some water's spraying out. dV dt equals -4. How fast is the height of the water changing? Well, in this situation, we're going to need a formula for the volume of a cylinder. And that's going to be pi times radius squared times height. Okay. But if you look, here is where the radius is 2. Here also the radius is 2. Everywhere the radius is 2. So dr dt is going to be 0. And at this point, you got a couple of options. I think this is probably something I'm going to be talking to you about in class next time. But on one hand, you could use the product rule, or maybe I'll do both, just because you're doing the extra practice, you're interested, and this is where we're headed anyway. On one hand, I can just use product rule. And so dV dt will equal the derivative of pi r squared with respect to t is 2 pi r dr dt, leave h the same. And then leave pi r squared the same and take the derivative of h. But since dr dt is 0, this whole term goes away, and I get pi r squared dH dt. Yes. Or you could just say, well, if dr dt is 0, r is a constant, so we could just substitute on r. In that case, we just plug in 4 for r. We say v is equal to 4 pi h. And then dV dt is equal to 4 pi dH dt, which is the same thing we're going to get over here when we plug in r equals 2, right? It really doesn't matter. So either way, I'm looking for dH dt. I've got dV dt is -4. I'm going to cover up the statement of the question. I think that'll be all right for you. -4 equals 4 pi dH dt is what I'm hoping to look for. And so I'm going to conclude right here at the bottom of my shot that this is -1 over pi. All right. And yeah, that's all for this set of related rates problems. It's definitely possible that I'll come back with yet another set of related rate practice problems. I think I'm going to just save, if I'm going to record another video, I'm going to kind of move away from the sphere, circle, cube, rectangle, kind of direct relationships, and focus on the cone, the proportional triangle, the more advanced related rate scenarios in the next video. But thanks for watching.